Every year, roughly 35 billion tons of carbon dioxide are released into the atmosphere as a result of the burning of fossil fuels, mainly coal, oil and gas. And every year this amount increases as a result of the increasing energy demand in the world. To curb carbon emissions and global warming, the International Energy Agency has set an ambitious roadmap to achieve net zero emissions by mid-century, while ensuring a stable and affordable energy supply. If managed sustainably, biofuels are renewable energy resources for heat, power and transportation that can contribute significantly to replacing fossil fuels and achieving a neutral sea energy system over the coming decades. However, as of 2021, the adoption of biofuels falls short of the predicted expectations. To increase the use of biofuels, it is mandatory to achieve performance breakthroughs and cost reductions for large-scale production of advanced biofuels. Microalgae are one of nature's best examples of solar energy conversion systems, transforming carbon dioxide into biomass through photosynthesis. They're capable of achieving photosynthetic conversion efficiencies up to 4 times higher than terrestrial crops, which means they require 10 to 50 times less surface area to produce the same amount of biomass. Due to their outstanding photosynthetic yields and ability to grow using non-potable water sources, there is much interest in the use of microalgae as a source of truly sustainable bioenergy feedstock. Anaerobic digestion is the most economically attractive process for the production of biofuel from microalgae, since it does not require drying of biomass, allows the recovery of essential nutrients, and it is a relatively simple procedure from an infrastructure perspective. Anaerobic digestion is a natural biomass degradation process carried out by microorganisms, which very efficiently transform the organic matter into methane-rich biogas in the absence of oxygen. This biochemical process has operated in soils and sediments for hundreds of millions of years, resulting in vast deposits of natural gas deep underground. Today, we can artificially accelerate these natural processes in order to produce a truly sustainable source of environmentally friendly biogas. However, neither of these processes is yet optimized for large-scale applications, leading to unfavorable economics. For centuries, conventional agriculture has struggled against the attack of pests and diseases. Decades of agricultural research have enabled the development of crop protection strategies that have resulted in previously unthinkable crop yields. Algae culture, the cultivation of microalgae, has incredible potential to become an important source of biomass for the future. However, the large-scale deployment of algae culture suffers at present from the same problems that conventional agriculture has faced for centuries. Pests and diseases, including viruses, bacteria, parasites and herbivores, can spoil microalgae crops in a matter of days. The performance of the anaerobic digestion process also depends on the functioning of complex microbial communities, bacteria and archaea, which control the efficiency with which the biomass is finally converted into biogas. Changes in the ecological and biochemical linkages within these communities can lead to process failure, thus limiting biogas production per unit of feedstock supplied. We can predict the failure of the processes by improving our understanding of cause-effect interactions between the different components making up bio-based production systems. By combining time series data and state-of-the-art mathematical methods for causal inference, we can develop warning signals that allow us to anticipate when the system is going to fail. Having a repertory of early warning signals for better monitoring and control will improve the cost efficiency of biogas production from microalgae biomass, as well as many other environmental and social benefits derived from the large-scale deployment of green fuel technologies. This is essential to contribute the targets of achieving a net zero emissions energy system by mid-century. Just as agriculture represented a momentous change in the history of humankind and of planet Earth, the expansion of algae culture and its use as a source of biomass are called to play a crucial role in the evolution of our society towards a more habitable future planet.